This is my fourth talk, my last talk. I thought it would be apt to actually bring something from my maths experience. And so I thought I'd do something that I can start from primary school and then maybe get up to where I am now in fourth year. So I think we're about half first years in here, are we? We've got quite a lot of first years and a few second years. But first year is really the first time that you actually see sort of these sets, right? Oh, I missed one. I don't know what it is about Q that I always forget. And maybe we've been dealing with most of these for most of our lives. Maybe not C. Maybe some people see that in A levels. Some people don't see it until first year of their maths degree. But mostly is we're comfortable with. You can kind of, but you can actually look at these as sort of levels in school if you think about it. I mean, in primary school, when you're first introduced to sort of addition, you only really start with sort of things like 2 plus 2, right? And then maybe you see a bit of 3 minus 1 because you remember what you add to 1 to get 3. But your teachers kind of tell you, you're not allowed to do this. You're not allowed to take a big number from a small number.
Yeah.
Which of course now we know is a lie. Not quite as heartbreaking as the Santa Claus revelation. But still, you know, your teachers lied to you at that point. But kind of looking back on it, it's something that was actually we were kind of working in N, weren't we? You could do some things, but there were some things you couldn't do. And kind of the same with multiplication. Maybe you saw 2 times 2, and maybe you saw 6 divided by 2, but you certainly never saw 1 divided by 3. I don't know why I keep using 1 and 3. And later, maybe we actually start working in the integers, but it's only when we start getting into the rationals that we actually start going there. Maybe around this time we saw some squaring, and a bit like backwards, sort of reverse engineering. If you know that 5 squared is 25, then you know what the square root of 25 is. Yeah. But the square root of 2 is an absolute mystery.
Irrational number.
Sorry?
It's an irrational number.
Yeah. And we start going into the reals. So it's only really until sort of either A levels or first year maths that we start getting into complex numbers, and you start realizing actually your teachers lie to you again. You can take the square root of a negative number. Now, there is a point to this because I don't know. I had one person in my A-level class who used to make a joke, and the teacher would say, "No, you can't do that." And he would say, "Oh yeah, you can." And it was something a bit like this, you know, your teachers lie to you kind of thing. Where's the duster? You just have to work in a slightly bigger set. But in order to get there, you also need... Where am I going with this? This is where the lack of practice is starting to hit me. In order to... Maybe I'll just introduce the set, rather than try and introduce it really cleverly. We call the set sigma. and you can model that in a few different ways, but the most fun way, I think, is called the Riemann sphere, like this. And what sigma is, it's a bit like each one of those is a little bit bigger than, includes a few things than, I can't say bigger, can I? But it includes a little bit more than the set before it, because it includes infinity. And it works like this. I don't know why I put that one up higher up, but it works as a continuous mapping jargon between the entire complex plane and sphere, like this, which is a little bit odd to get your head around. I considered bringing in football today to try and. So it's not. You can't think of it as a finite sphere, because, of course, as you get further up here, all of a sudden it starts getting denser and denser and denser. If this is the point to infinity. Down here, everything is quite nice. This is where the sphere intersects with the complex plane. This is where the lack of practice is heading me. This is the complex plane. This is C. This is the unit circle. And this is the unit sphere in, I suppose, R3. I mean, we've... Oops. So, if that's the x-axis, that's 1, that's -1 in the y-axis, or minus I in complex. So, what we do is we take a line from the North Pole to every point in the complex plane. And that line will intersect the sphere at exactly one point, right? So, and what that gives us is a unique mapping between the sphere and the complex plane. So, does that make sense so far, that every point in the plane has a point in the sphere, except this point, which just straight parallel, and we just, well, I suppose all the way around, which never intersects C, but we say that it goes to infinity in sigma. So sigma equals, you are allowed to heckle, by the way, fourth years, if you think I've done something there.
So I suppose the point is, as P goes off on the real line, like 1, 2, 3 and so on, the Q is going nearer and nearer to the North Pole. But there's no point on this real plane that actually corresponds to hitting exactly N. So as you're taking the limit of P going further and further away, you're getting closer, and the Q is moving closer and closer to that N. So that's the idea. I like your pictures. I'm just trying to explain.
Yeah. Sorry. Yeah. Thanks, Charles. So this is also quite a nice object in topology. Has everyone heard the word topology?
Topology.
Yeah. But you haven't studied. Some of you haven't studied it yet. So some of the third year modules, when you get past some of the nice stuff, you actually have to start getting in. And second year as well. You actually have to start getting in some of the terms and know how to do some of the nice stuff. But at the moment, we can just look at the nice stuff. In topology, we mainly look at things that can be continuously mapped onto each other. Charles is looking at me skeptically. Sorry, no. So what do I mean by that? I mean, sort of, if I've got a disk and I've got a smaller disk, there is an easy way to continuously map those, right? I just push everything close towards the center. To the extent that you could even say that the disk you can also continuously map to a point, in which case you would call that contractible, for the obvious reason that you can contract it into a point. But if I, say, cut a hole into that disk, all of a sudden that now goes into a circle, but there's this discontinuity in here. So you can't continuously deform that into a point in the same way. There's always going to be that hole that you can't get rid of. And so that invites all kinds of nice things, and including the joke, I think you can tell a topologist because he can't tell the difference between a coffee cup and a donut. I think most people got that. So what this implies, or what this relies on, is that if you just were looking at C as just a whole plane, then really you could just continuously deform that into just a point. But with this added point, sort of off at infinity, that joins all the edges up, you can look at that as a continuous sphere. Yeah, does that kind of make sense? So, so that's what it uses. What can we? But like, how accurate can we make this? I mean, you've got. I mean, it looks very theoretical at this point. I mean, we've got these bits all the way in infinity, but we've also got that precision there because we actually have an actual line. We know where that sphere is in R3, and we know where that circle is in R3, and we know where that line is. Maybe I don't need that yet. Actually, I'm gonna see if anyone else can work this out. I've got that sphere. I've got the unit sphere, and it intersects at the unit circle, and its own equator. And I've got this line that goes through both points. Say n is at 0, 0, 1. So this is the z-axis, or x3z. P is at something, say x, y, 0, where it's in the complex plane. So really that's equivalent to some complex number. I won't use z. Omega equals x plus iy, right? and we've got Q as some x1, x2, x3, where yeah, that's all that's what we know about those points, and about that line. Can anyone think of a way of finding out? Should we say? Well, can anyone find a relation between x1, x2, x3, and x and y?
X is equal to x1 over 1 minus x3, and y is equal to x2 over 1 minus x3.
I think that's exactly right. Is that something you remembered, or is that something?
Yes, I just did this about 2 weeks ago.
Ah,
I've got a test on it tomorrow.
Okay. So we can use the fact that they're on a line, and they're on the same line, and so we can think of the fact that we can use the fact that NP is basically a scalar multiple of NQ, right? Which gives us that. What's NP? That's going to be x minus 0, y minus 0, and 0 minus 1. And x1 minus 0, x2 minus 0, and x3 minus 1. Which means minus 1 over. Yeah? Really, lambda I just included to sort of illustrate the point, but that means that we now have this. And it means that we can now work out what our actual math, which I think we tend to call pi. I think that's right. So what does that give us? So x equals x1 over 1 minus x3, like you said, and y equals x2 over 1 minus x3. Or what's the other way? Can you bring? Sorry, I'm not trying to remember to do it the other way. I'll check the book. And x3. Yeah? So that's a minus. Is that okay? Sorry. So what is the point in all this? I mean, it's very nice theoretically, but what can we do? I mean, in second year, you probably have the opportunity to study a little bit of complex functions. just in C. And one of the big things about studying functions in the complex plane is differentiability, which you've probably already seen by now in first year. You've maybe seen the Cauchy-Riemann equations. So occasionally, you get things which are completely differentiable everywhere, but as likely as not, you're probably going to have some things with things we call singularities. In second year, you actually learn, just because there is like a few places where it's not differentiable doesn't mean we can't do anything with that. We can work around what we call singularities. And sorry, I hope you don't mind if I rub this off. So you don't have to have this point at infinity to be able to do things with functions in the complex plane. But the nice thing about having that infinite point is that even if you have, say, so like that, in the complex plane, that would be a singularity at A, because that goes over to 1 over 0 in infinity. It goes over to 1 over 0 at A, sorry. In sigma, it just goes to another point in the space. It just goes to infinity, which is just another point. But so that opens up a lot more doors, but you end up sort of maybe you get sort of scary things like sort of n or something like that, and all of a sudden you can start looking at things that before you were too sort of you could sort of work around in C, but in sigma all of a sudden we can work with them. But you end up sort of turning the sphere in on itself, which I don't want to go to. I won't go too deeply into that. Yeah.
One thing I'm slightly confused by. So you talked about the point where it goes to 1 over 0. Isn't that undefined and not infinity because the limits are inconsistent? So the system defines itself at infinity, which is perfect. But 1 over 0 doesn't always go to infinity. It goes to minus infinity or infinity, depending on which direction you take the limits from.
The point is that sigma has the point infinity and that's it. So you've only got this point infinity.
So would, in this system, in that case, would it always just go to infinity?
Yes, because no matter which direction it went into, it would always come back to this point.
Right.
It always just goes off the plane somewhere towards infinity.
If you picture it moving towards the point at infinity on the sphere, it doesn't matter which way it's going to an awful from, you always get there.
Yeah, exactly.
So Peter kind of mentioned this earlier when you were saying you're taking all of the boundary of C and like wrapping it up.
So even though there is an inconsistency in the limit, it doesn't really matter for this system.
Yeah. Exactly.
But it's not an inconsistency because minus infinity is the same as infinity. It's just one point.
Yeah. But of course, in C, infinity doesn't really exist. It's just kind of something we use, and that's something like we were already seeing in A levels. You didn't. You sort of said things tail off to infinity, but you didn't actually mean a number. You just meant that it diverges. Which is why when my friend in my A-level maths said that 1 over 0 is infinity, of course the teacher had to say, no, it doesn't. even though really, if you go up to sigma, then he's lying. I think that's kind of taken us past second year. That's gone up to these singularities that you see in second year. I can't remember whether we do anything in third year, but we start going more into sort of that topology. In fourth year, where we've actually gotten more into like what we can do with these kind of functions, we've actually started studying what kind of happens when you have sort of infinite singularities, and into things called periodic functions, at which point you can start breaking up the plane into a lattice, like a grid. And it's I don't think anyone will have seen anything like that this year because we haven't had a talk on wallpaper groups. I think it's the first year we haven't had a talk on wallpaper groups. But which is a shame because I studied wallpaper groups and they're really nice. That we can start looking at functions, say f, which is, and we would say f is periodic, is omega periodic, if omega was the smallest non-zero number such that happens, right?
For all Z, right?
For all Z, yeah. And that's something that we're used to, sort of like the cosine functions. Right? So sine and cosine function, they're 2 pi periodic. No, 2 pi periodic. 2 pi periodic. That's embarrassing. One of the two. Either way, if you add 2 pi, if you have cosine of x plus 2 pi, you get cosine of x, right? In sigma, we've been studying for a while. We're now finally getting into some actual functions because there's actually a lot you can do just with the theory of periodic functions. We've been studying for a while the idea of actually having, because we're working in a plane, some omega 1 and omega 2, so that it's doubly periodic. So if I have f of z here, and I go up omega 2, then I get the same thing up there, and the same thing there, and the same thing there, and the same thing there. So if that's, can you kind of imagine that in your head? And so we're trying to build up functions that have singularities an infinite number of places, but they do it periodically, like that. Yeah, so maybe it's best to edit there. But that's where we're just getting to now. We've defined some functions. We've defined a few functions called a Weierstrass P function and sigma. I think is there a zeta? Something. I think it's zeta. I write it like that. I know some people write it differently. Yeah, that's kind of where I've gotten to. Where I don't know how to end it now. That's the one. That's the one thing I hadn't thought about. But so I don't know how many people are planning on doing fourth year, but I wanted to try and give an expectation of where you can be by the end of a third year or 4 year degree. Hope you enjoyed a little slice of that. Anyway, thank you.
Thank you for that, Peter. Does anyone have any questions? In which case, I have a question.
Yeah.
Is there some kind of alternative that you can invent where infinity does have an argument, so to speak? So it is dependent on which direction you head off in. Is that something that appears at any point? Kind of goes out to Charles as well.
I was worried you said that.
That's a good question.
I was going to ask a similar question.
If you've not encountered it, then you've not encountered it.
No, I don't think I have. Yeah.
So I think what you might be looking for is maybe p-adic numbers. And if Hector's here, then I give it to him because he does these things. So
Who, sorry?
Hector.
Okay.
So there's a way of going from R. So what you're really doing with this is you sometimes call it compactification. So when you've got C, you haven't got a boundary. Right? You can go off anywhere. When you've got a sphere, there is sort of, it lies in R3 and it has a boundary, right? So what you're making it is you're making a boundary and also it's closed in a topological sense, but we don't do topology, that's good. Right. So can you compactify anything else would have been one question. And
Yeah.
filling in the gaps in some way is a way from going from R to C is one way of filling in the gaps as far as sequences goes. And p-adic numbers are another way of filling in the gaps. So they use a different metric on R. But I don't know enough to tell you something interesting about them. They're quite strange. You can look up a Wikipedia article. I don't know if there's another. I don't think there's another compactification of C.
No, I don't think so. I don't. No,
I think it's.
So what was it? P-adic.
Yeah, you can look at p-adic numbers. So that's a way of filling in the holes of R.
Was it P?
So you get AD IC. Yeah. So you pick a prime P, and then it's a way of filling in the holes that you get in R. So the way I think that's right. Or maybe you start with Z and it's a way of filling in the holes. Generally, it's denoted ZP. I guess maybe it's Z. Sorry, I'm not more useful.
Are there any other questions? Go for it.
Apart from quantum mechanics, what are the other applications of the Riemann sphere?
I don't know. So, does anyone seen any applications? No.
So using geometry maybe.
Yeah.
Circles and lines map to lines and circles. And if you have a circle on the Riemann sphere, they map to. You have a big, is it a great circle? We have
Yeah.
a circle across the whole sphere. It would map to a line and a projection. And then circles map to circles.
Yeah.
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 It represents circles and lines in C. It's basically the same thing on the Riemann sphere.
Yeah. So you do. I'm afraid that's as far as applications go. You do see it a lot more in geometry and a little bit in sort of metric spaces, which is quite geometric. Yeah, and to that extent, but I'm a very pure mathematician.
Oh, okay.
Applications aren't really my thing. Sorry.